Welcome back to Zero Dark Emissions. Last time we left off with the low voltage system after completing the rolling chassis, and now that our equipment arrived, we can finally start the EV portion of the build. Today I'm going to start by talking about the selection process for the motors, inverters, and gearboxes before we get to the actual installation of these items. So as discussed in earlier episodes, my basic setup will be to have two motors, one at each axle. The idea will be to run the rear motor only for normal road use, and then use both the front and rear motors for four-wheel drive applications. Instead of a transfer case, our change from two-wheel drive to four-wheel drive will be handled by turning on and engaging the front motor. Each of the two motors will be located upstream of the differentials, which accomplishes two things. First, and most obviously, keeping the differentials handles what any differential handles in that it allows the opposing wheels at each side to turn at different rates when turning. But secondly, it also provides a gear reduction, which is a really important part of our equation. The three most important pieces of the motor selection for me are peak motor power, mostly in the form of torque, maximum motor speed, and the physical size of the motor in order to configure within my space constraints. My goal is to achieve the same or better torque and speed as the original Humvee. So with this in mind, I developed a spreadsheet where I could test various motors along with various gearing in order to find the right torque to speed balance. In the context of electric vehicles, most electric motors have less torque than needed but also operate at a higher top speed than needed. So although we do not need a multi-gear transmission in the same sense that an internal combustion engine requires it, since unlike an ICE, an electric motor has 100% torque at the first RPM, we will still need a single gearbox to gear down the motors to get the right torque to speed combination. In my specific case with the Humvee, I am looking for even more torque than most EVs, but also don't need as much speed, meaning that I am looking for a relatively high gear reduction ratio. Fortunately, the Humvee has some natural advantages. In addition to the diff, which has a gear reduction of 2.73 to 1, we also have the geared hubs, which have a reduction of 1.92 to 1. To these existing factors, we will be adding a new 3 to 1 gearbox at each motor, which gives us an overall reduction of 15.72 to 1. So after plugging in a number of different motor options, I landed on the Cascadia Motion SS250. This motor has a peak torque of 500 Newton meters or 368 foot-pounds and a maximum speed of 11,000 RPM. When used in combination with my overall gear reduction of 15.72 to 1, this gives me a peak torque of 15,724 Newton meters or 11,597 foot-pounds, with both motors utilized, and a maximum speed of 77 miles per hour, which is more than enough speed for my Humvee. To put this in terms of horsepower, each of my motors have a peak of 275 horsepower, which is 550 horsepower total, versus the 160 horsepower of my old diesel engine, and will be much, much more efficient. Okay, so these motors have the numbers that I need, and the size is relatively compact and fits well within my available space. So now I need a gearbox that gives me the 3 to 1 reduction. I started by looking at the torque box by Torque Trends, but initially they only had a maximum gear reduction of 1.9 to 1. Then, almost as though they were reading my mind, they posted that they were developing a 3.0 to 1 torque box that would be ready in a few months, so this was exactly what I needed. One additional detail regarding the gearboxes. The torque boxes are available with a slip yoke output as well as a fixed yoke output. I was initially looking at going with slip yokes for both the front and rear, since this would give me good tolerance control for mounting in that direction, but after further discussion with the manufacturer, it was made clear that the fixed yoke option could handle more torque than the slip yoke. So I decided to use a fixed yoke at the rear, where I would require more torque when the rear is handling the full load, and where I could make the fixed yoke work, but a slip yoke at the front where this would theoretically only ever be taking half the load, and because I need the slip configuration, which I will cover later when we get to the front. The supplier actually supplied a flange output instead of the fixed yoke output, but this actually worked out better for me, which I will cover in a minute. The final main component is the inverters. This is what takes the DC from our batteries and converts it to AC for our AC motors. The Cascadia SS250 offers a combined motor inverter unit with the inverter situated on top of the motor, but this did not configure for me in my limited space, so I opted for a separate set of inverters which will be located under the hood. These inverters are actually motor controllers in addition to inverters, and we will get more into that in a future episode. There's one more small but important item that I need now, which is a drive disconnect at the front for when we are in two-wheel drive. It is possible to just not operate the front motor when in two-wheel drive, but this would mean that the motor would be turning all of the time, driven by the turning front wheels while moving down the road, and would provide drag on vehicle efficiency as well as some other complications with regard to feeding electricity back into the batteries, since this motor would be acting as a generator. So we will want to physically disconnect the drive of this motor when in two-wheel drive. I will get into more details about the front disconnect in the next episode when we handle the front. So with the equipment selected, purchased, and delivered, the next thing is designing and fabricating the motor and gearbox mounts. Here in section you can see how we will be mounting the motor. We will essentially have motor mounts consisting of a 1/4 inch thick steel plate at the back of the motor as well as the back of the gearbox where it interfaces with the motor. The one at the gearbox side is actually a single plate spanning across to both frame rails, whereas the ones at the front motor side are 2 independent mounts on each side. Each of these mounts will have mounting holes that align with the threaded mounting holes at the motor and gearbox, and will extend to bushings that will attach to bushing mount brackets at the frame. This keeps the motor isolated from the rest of the vehicle to limit vibrations from the vehicle to the motor and vice versa. In order to have these bushing mount brackets fabricated with the bends, I needed to make them in 2 matching parts, since both bends would not be able to be made on a single part due to the close proximity of these bends. So now I need to weld these brackets together. I started by grinding down the interface edges to allow room for and to get full penetration of the weld. For the mount at the gearbox side, I will be making use of the existing body mount bolts for attachment, which were luckily in almost the perfect position. I'm starting here by grinding down these areas where the mounting hole tubes projected in so that I get a flush condition. The body mounts use through bolts at the driver's side, which actually perform double duty as connections for exhaust support mounts on both the inside and outside of the frame rail. But at the passenger side, the body mount bolts are threaded into the frame from the outside. So at the passenger side, I need to drill out 2 of these 3 holes so that I can through bolt the body mounts along with the motor mount brackets. The 3rd hole will remain threaded for the body mount only. For the bushing mount brackets at the other side of the motor, I will need to drill new holes at the main chassis rails and weld in short sections of steel pipe so that I can tighten the bolts for these mounts without crushing in the frame. The locations of these holes are measured off the gearbox side mounts already located. The brackets will be attached with 2 1/2-inch bolts, so I'm using a 3/4 steel pipe with an inner diameter of 0.510, which is perfect for my 1/2-inch bolts. Before drilling the 3/4 inch holes, I am first drilling a pilot hole through both sides so that the holes are aligned. After getting the holes drilled on the marked side, I am using a long bit to transfer this hole to the opposite side of the frame. Now with the pilot holes drilled, we can drill out the 3/4 inch hole from each side. Now here are sections of the 3/4 inch pipe cut at a length that is slightly longer than the width of the frame and inserted into the holes. I've also grinded away the paint in this area in order to have a clean weld. With the pipe welded in, I can now grind down flush with the frame. We will touch up the paint at the chassis when we paint the other new components. In order to get good measurements for our motor mounts, we will now temporarily install the motor mount brackets. Note that the brackets are being installed with the mounting bolts centered in the elongated holes so that I have maximum adjustment in the vertical direction, and with a 1/8 inch shim plate at each side so that I have some lateral tolerance to back out if needed. I can also add shims if needed. This, along with the elongated holes in the brackets in this direction, give me good tolerance in this left-right direction. Since I do not have a slip connection at the rear, longitudinal tolerance is achieved via a flange shim plate between the flange output on the gearbox and the flange yoke. This is the advantage of the flange output versus fixed yoke output that I mentioned earlier. The shim can be eliminated, reduced, or added to as necessary. So now we have all 4 bushings located in space relative to each other and relative to the differential U-joint and to the motor and gearbox mounting points in all 3 directions. This gives us all of the required points in space to design the motor mounts and to have them fabricated. I'm starting out in CAD designing the mounts based on the various points measured, and then bringing this into Fusion 360 to model the parts and add bends to provide some stiffness in that direction. This is the one at the gearbox side, and here are the 2 at the opposite side of the motor. And here we have the fabricated mounts, which we will temporarily install on the motor and gearbox so that we can temporarily put in position with the bushings. The one at the gearbox side is already on, and the bolts that attach this are also the bolts that attach the gearbox to the motor. One of these bolts is not used for the mount attachment since the park lock interferes in this area, so that one bolt is only used for the attachment of the gearbox to the motor. Now we will place the 2 at the motor side. Note the 2 holes in the driver's side motor mount, which are there to allow passage of the 2 coolant lines from the motor, as well as the temporary install of the lifting ring. Before putting the motor and gearbox into position, we'll first install the U-joint and flange yoke to accept the motor and gearbox when put into position. Here's a look at the shim plate at the flange yoke to give us tolerance in this direction. With the connection made at the U-joint, we can now install the bushings, adjusting the bracket shims as needed for a snug fit. Note that I have aluminum mock-up bushings installed for now, so as not to melt the actual poly bushings. My measurements were pretty good for the most part, although you can see at this one location I needed to remove the shim to get a good fit. This is exactly why we started with the shims to begin with, so that we have something to back out if needed. I also needed to add additional shims at this location. Now we can tack weld the motor mounts to the bushing housings. Prior to welding, I am ensuring a tight fit between the bushing housings and the motor mounts by prying the bushing housings against their curved counterpart at the motor mounts. With all bushing housings now tacked to the motor mounts, we will remove the motor and gearbox and disassemble everything for final welding. With everything fully welded, we can clean and paint the motor mounts, brackets, and touch up at the frame. We are using the same paint that we used at the chassis, which is the Rust Blast system, including the basic Rust Blast coating along with top coat in satin black. Finally, we can install the motor and gearbox along with the universal joint connection, trimming the bushing brackets as needed. Note that the bolts at the bushings at the motor mounts towards the front do need to be installed from the rear side, since the battery box, once installed, will not allow these bolts to be pulled out from the front side if the motor ever needs to be removed. And now here is the completed rear motor and gearbox installation. Note that the rear gearbox has a park lock to lock the gearbox when in park. There will be an actuator to operate this park lock via the shifter switch that we covered in the last episode, and we will take the installation of this actuator in a future episode, as well as the vent line connections at the motor and gearbox. So next time we will cover the installation at the front, which will not just cover the front motor and gearbox, but also the installation of the front drive disconnect. See you next time.